Dr. Singh doesn't have any issues.
Are you able to see my this thing slide?
Yes, yes,
Yeah.
we can see.
Just wait, let me go for slide. So. Are you able to see it now?
Oh, it's still in the PPT mode.
So you have to share your full screen.
Screen, okay, not in this.
Yeah, not the tab alone, because sometimes it doesn't.
Okay, okay, fine. So
you can stop sharing and reshare.
correct. Entire screen. Share. Now, are you able to see the slides?
Yeah, slides we can see, and also the full screen. Yeah, thanks.
I've gone to the next slide. Are you able to see next slide also?
Yes. The first slide, now the next slide. Yeah, there is a little bit lag, but it's fine. Yeah.
Okay, fine. Yeah. We're going to start now.
Yeah, so let me just introduce you and then we can get started. Is that okay, Professor Raghu Prakash?
Yeah, fine. No problems. Please go ahead. Yeah.
Thanks. Yeah, sorry for the slight delay in beginning the webinar. It's my pleasure to again welcome Dr.R Singh, who's speaking today. Dr. Singh graduated from BIT Sindri in 1988 and obtained his PhD from IIT Bombay, where I currently am, in 2003. He joined the metallurgy division of BARC in 1990 and has been there, I think, since then. He has carried out extensive work on development of fabrication route for zirconium alloy pressure tubes and various aspects of hydride-induced degradation of mechanical and physical properties of zirconium alloys, where he has used both experimental and computational approaches. He has contributed to the safety assessment and life extension of the pressure tubes of Indian PHWRs. Dr. Singh has been awarded with many awards and fellowships, notably the Humboldt Fellowship between 2004-05, the Marie Curie Incoming International Fellowship in 2005-08, and the DAE Scientific Excellence Award in 2000, as the Technology Award in 2017 as well. He's a life member of the Indian Institute of Metals, the Indian Nuclear Society, and the Materials Research Society of India. He has published over 150 articles and several other conference proceedings and technical papers. Presently, he is serving as the head of the Mechanical Metallurgy Division, Materials Group of BARC Mumbai. And today he will be talking to us about some of the studies that he and his group has been doing on hydrogen or hydride-induced fracture behavior in a zirconium niobium-based alloy. So with that, I will leave the stage to you. Thanks.
Thank you, Professor Jaya, for your kind introduction. In fact, just before we start the presentation, I have brought out that what we do in Mechanical Metallurgy Division. So basically, we perform basic studies on materials deformation, evaluation of mechanical properties, and their correlation with processing parameters, microstructure, and alloy chemistry. We use both experimental and computational approaches for this work. Our input is required for manufacture of components with enhanced life, its life extension, and safety assessment of the component during service. Our expertise is sought by various units of DAE like NPCL, NFC, Heavy Water Board, Atomic Energy Regulatory Board, and various divisions of BARC. Am I audible enough?
Yes.
Yes, yes, everything is
Yeah, yes, sir.
Yeah, so major R&D activities being pursued by my division is that there are 4 major categories. The first is new generation zirconium and titanium alloys for various reactor applications. Second one is super alloys and borated steels, again for nuclear application. Nuclear structure steels, refractive metals, alloys, and metals and alloys, development of these materials. And finally, fourth group is technology development for nuclear and aerospace application. Materials of interest to us are zirconium alloys, titanium alloys, RPV steel, cobalt-free merging steel, alloy 625, alloy 690, alloy 693, alloy C2000, C2000, nickel titanium shape memory alloys, which earlier Dr. Madhur Gopal was working, and now my colleague Dr. Vikas Manji is continuing this work. Refractory metals and alloys for compact high temperature reactor, max phase ceramics for accident tolerant cladding. Again, I think Fekral is also for same purpose. I think today's talk, I have given the topic, the influence of hydrogen or hydride on fracture behavior of zirconium, 2.5 IBM pressure material. However, I think my concern about whatever work we have done, based on that, now we are all talking about hydrogen economy. So I just wanted to just flag this issue and suggest what are the areas in which we mechanical metallurgists or those who are concerned with the structural integrity should be working. So this is my personal view. It is not my department's view. So I think before I go on the actual topic of this hydride emitter of zirconium IBM alloy, I'll be talking a little bit about hydrogen economy, present various mechanisms of this in hydrogen or hydride embrittlement, and finally I'll come to fracture behavior of this alloy. So in hydrogen economy, to arrest the effects of climate change, United Nations has identified 17 sustainable development goals. Goal 7 aims to provide clean and affordable energy. Over the next few decades, hydrogen economy can either partially or fully replace fossil fuel economy. Now, this third statement is very powerful statement, and I've tried to summarize what is the present status of this. So if you see this production, packaging, storage, transfer, and delivery of hydrogen are all energy consuming steps. Over the next decade, competition between adherence to idealistic scientific goal of replacing fossil fuels with hydrogen and finding practical economic solution involving a combination of several technologies will decide the growth of hydrogen economy. One of the options which is being seriously being explored is the combination of hydrogen, renewables, and energy storage systems. Overall life cycle cost of technology used in hydrogen economy for hydrogen generation, storage, transportation, and consumption will depend on the preference of materials of construction used in these stages of hydrogen economy. So these are the 4 stages for the hydrogen generation, storage, transportation, and use. So coal, oil, and this thing, steam and reforming, still they are the 2 major forms in which hydrogen is being generated. But water electrolysis has got a scale-up advantage. If it can be adopted, then large-scale hydrogen production can be achieved. And this water electrolysis can be done by obtaining electricity either from nuclear, solar, wind, hydro, and wave. Water splitting using thermal heat is also possible. Again, heat can be provided by nuclear or solar sources. Biomass fermentation and its pyrolysis, that is another method of hydrogen generation. For storage, I think usually hydrogen can be used either in pure form, so without any transformation. So gaseous hydrogen at very high pressure, or liquid hydrogen at low temperature, or a combination of both low temperature and high pressure, that is again gaseous hydrogen. It can also be stored in metallic lattice. It can be stored in the form of chemical forms like ammonia, methane, or methyl alcohol, and synthetic fuels, green ammonia. So these are the methods in which it can be stored. Each method has got its own advantage and disadvantage. We'll cover it later. So transportation, gaseous hydrogen and liquid hydrogen can be transported in the form of tankers or pipeline or trailer. And end use, like a stationary hydrogen used in refineries for production of steel. Now it is being considered for chemical industries. Now it is for a stationary application for generating heat and electricity, especially for colder country and all. And for transport application like shipping, aviation, aerospace, rail, trucks, buses, and cars. For aerospace industry, in cryogenic engine, hydrogen is already being used as a fuel. For energy storage and grid stability, especially for renewables, this is another use of hydrogen. For hydrogen, I think different color codes are being used, being followed. However, there is no standard on this. So first one is that gray hydrogen, which is generated from fossil fuels with CO2 emission, and there is no output is again hydrogen gas and CO2, so there is no effort to capture the carbon dioxide produced in this process. So this is all gray hydrogen. This is not leading to any change in environmental impact because CO2 is already being, it does not reduce the impact of CO2 on the environment. So, but if you produce hydrogen from the fossil fuels only by capturing this carbon dioxide to hydrogen, but here also it is not full capture, it's partial capture only. Now, pyrolysis of fossil fuels, natural gas plus air, that is the input, and you subject it to high temperature exposure, and the output is hydrogen plus carbon in solid form. So here, I think entire carbon is getting captured. So this is good for the environment. And now, third one, last one is electrolysis. And depending on the source of electricity, we have got different color codes. Green hydrogen is the one, green electrolysis is the one where electricity is obtained from renewables. And pink is the one where electricity is obtained from nuclear. And yellow is the one where electricity is obtained from solar grid. And ultimately, in all these cases, we have got hydrogen and oxygen which is being produced. But presently, global hydrogen production from natural gas and coal is about 76 and 23% respectively. Approximately only 1% of the hydrogen comes as a byproduct of alkaline electrolysis used to produce chlorine and sodium hydroxide, and only 0.1% of hydrogen produced are by water electrolysis. Now, next few slides, I will just show where I will show the environment in which material of construction has to use. If you talk about a steam methane reforming method, here a plot shows the rate of methane reforming with temperature. And as you increase the pressure, you can see that the yield increases, but then I think temperature of operation is also increasing. So the message I want to convey from this slide is that if we note the temperature, which is ranging from 300 to 1100 degrees Celsius, and the pressure is about up to 100 bar. Another method of producing hydrogen is the thermochemical hydrogen production. Here you have got a reactor which performs multi-stage reactions with no net consumption of chemicals. The input is water plus high temperature heat, and output is hydrogen, oxygen, and low temperature heat. One example of thermochemical hydrogen production is sulfur iodine process. Here, first 3 reactions takes place. First one is a Bunsen reaction where iodine and sulfur dioxide combine with water to form hydrogen iodide and sulfuric acid at low temperature of 120 degrees Celsius. Second reaction is the hydrogen iodide decomposition, which takes place about 450 degrees Celsius. And third reaction is the sulfuric acid decomposition, which is taking place very high temperature of 850 degrees Celsius. And ultimately, the product, you can see both SO2 and I2 is getting recovered. So that's how this there is no net consumption of chemicals, and this kind of reaction can produce hydrogen. So input will be water plus high temperature heat, and output will be hydrogen, oxygen, and low temperature heat. The temperature over here is 120 to 850 degrees Celsius. Now, for electrolytic production of hydrogen, there are 3 methods. First is alkaline method, which is composed of again electrodes, a microporous separator, an aqueous alkaline electrolyte. In case of proton ion exchange membrane, platinum black is used, along with iridium, ruthenium, and rhodium for electrode catalyst, and Nephron membrane. For solid oxide electrolysis cells, we have got it is just SOFC working in a reverse. And you see the temperature. In the first case, the temperature is only 60 to 80 degrees Celsius. The pressure is up to 30 bar. Efficiency is about 60%, 60 to 70%. But capital investment is low. In case of proton ion exchange membrane, I think the temperature is again not much, 50 to 80 degrees Celsius. Pressure is 30 to slightly higher, 30 to 80. But if you see SOEC, there the operating temperature is 650 to 1000 degrees Celsius. And efficiency is also very high, 74 to 81%. And operating pressure is less. So various hydrogen methods are there. I think hydrogen storage methods are there. And whenever we talk about hydrogen storage, 2 parameters become important. One is gravimetric density, which is what the percentage weight of the hydrogen in the total matrix. And second is volumetric density, how much kg of hydrogen is stored in per meter cube. And these are the temperature and operating temperature and pressure. And advantage and disadvantage also has been listed here. The most commonly used method is still high pressure gas hydrogen cylinders. Here, gravimetric density is maximum 13%, and volumetric density is up to 40 kg per meter cube. This can be used at room temperature, and pressure could be as high as 1000 bar. Advantage is simple and well-developed technique. It has got very short refilling time, so this is the greatest advantage of high pressure cylinder. But then disadvantage is that it's got very high internal pressure, thick wall cylinder walls, so low density, large tank size is required, and risk of rupture and explosion is also there. So that is the disadvantage with high pressure hydrogen cylinders. Liquid hydrogen is also stored in cryogenic tanks. Gravimetric density depends on size. Volumetric density is much higher, 70.8 kg per meter cube. but temperature is minus 250 degrees Celsius. Pressure is not a concern, 1 bar. So it has got a very high hydrogen density, easy for transportation. And here also it has got a very short refilling time. But cost of refrigeration is required. Evaporation, leakage losses there. A structural failure of tanks under high stress, especially some of the BCC metals which who shows brittle behavior at low temperature. Now, adsorbed hydrogen in metallic lattice, mainly two types of metallic hydrides are there, AB5 and AB2, and the gravimetric density here is very low, only 2. However, volumetric density as high as 150 kg per meter cube can be achieved. Temperature is only 25 degrees Celsius. Pressure is also not a concern. High hydrogen density is the advantage. Good reversible hydrogen charge and discharging capability is there. It is more highly safe. So metallic hydrogen stored in metallic hydride as metallic hydride is highly safe. However, disadvantage that it has got high tank weight, low hydrogen release rate, heat generated during charging, and it has got very long refilling time. Weight ratio of hydrogen to storage system is less than 2% presently. And there is complex compounds like aluminum, ALH4, BH4, and here gravimetric density is as high as 18% can be achieved. Volumetric density is similar to metallic hydrides. Operating temperature is greater than 100 degrees Celsius. Pressure is low. It has got high hydrogen density. But here for desorption takes place at elevated temperature, and absorption takes place at higher pressure. Now in the literature, you will see that for hydrogen cylinder, we have got 5 class of cylinders. The first type 1, 2, 3, 4, and 5. These cylinders are made of steel or aluminium. And depending on material of construction, the pressure, maximum pressure which in hold is given over here. For aluminum, it could be 175 bar. In case of steel, it could be 200 bar. And this is already being used for submarine application. However, in order to increase the pressure, you can go for type 2 cylinder, where apart from this metal, some composite is used as a winding around the cylindrical portion of the tank. And here, the aluminum and glass combination, we can go up to 263 bar. For steel and carbon fiber combination, we can go up to 300 bar. This is also used for stationary fuel cells and all. In case of type 3 cylinder, there is a metal liner to prevent permeation of hydrogen. So this liner could be aluminum or steel, metal liner could be aluminum, copper and all. And composite which is used for fiber, that is fiberglass, it could be aramid or carbon fiber overwrap. And here pressure can go as high as 700 bar. And this is also being considered for use in vehicles. The last one, where instead of metallic liner, we can have a liner of polymer. And here the cylinder is made of carbon fiber overwrap and polymer liner. And that's why this is lightweight, and plus it has got capacity, it can hold hydrogen up to 350 to 700 bar. So this again application is vehicles only. And nowadays people are thinking of making the cylinder with fiber itself is a composite, and it can go up to 1000 bar, and this is being considered for aerospace application. Now the summary of this hydrogen storage systems is provided in this slide. On y-axis we have got volumetric density, and in x-axis we have gravimetric density. You can see here that liquid hydrogen is lying over here, and if you see any high Z element, if you want to store hydrogen in high Z element, definitely depending on the chemical formula, the gravimetric density will be limited. I think, but if you see this mixed hydride like magnesium borohydride, aluminum borohydride, ammonia borohydride and all, so all these things are having very high volumetric density and gravimetric density. And ultimately, this while picking up the material in which hydrogen can be stored in metal, one can always think of low Z element. That is what can find some application. This is the message coming out from this slide. Now, if you see hydrogen consumption, it can be used for transportation, for generating electricity for powering the vehicle. And some people are also thinking of using hydrogen for internal combustion engine itself, for SOFC and rocket fuel. It is already being used. The form in which it is used is gaseous hydrogen or liquid hydrogen. It is already being implemented and likely to be scaled up in near future. The fuel and feedstock for industry, it is used as a reagent or reductant for refining petroleum, producing fertilizer, other chemicals, steel, and processing of foods. Again, it is a form in which is used as gaseous hydrogen. So it is for reducing sulfur in petroleum, producing ammonia or methyl alcohol. Nowadays, already it has been demonstrated that it can be used for producing steel also, especially for reducing the and DRI, direct reduction of iron. It is used for converting unsaturated fats to saturated fats. And here I think one can think of captive, for all the uses of industry, one can think of captive hydrogen generation. Hydrogen is also used for hydrogen generation and grid balancing. Here direct combustion or SFC is the one, again gaseous form. So here it is considered for use as a replacement or supplement for fossil fuels, and fuel for residential and commercial buildings, direct combustion. So, and here it can be stored in storage tanks, especially for colder countries. So challenges posed by hydrogen are permission of hydrogen through materials, resulting in effective leak through the materials, degradation in mechanical properties of a structural material that compromises the structural integrity. Choice of material, thus the choice of material depends on the service conditions, mechanical, environmental, material condition, associated with the component used. Now, material testing, for material testing, hydrogen absorption, and diffusion out and diffusion in time, and test duration, that becomes important. Two types of test in hydrogen atmosphere can be done. The material can be directly tested in high pressure hydrogen gas. It is external source of hydrogen, or material can be pre-charged electrolytically with hydrogen, and the test can be carried out. Hydrogen diffusivity is very important. Like for austenitic stainless steel now, the diffusivity is less than 10⁻15 meters per second. So long time is required for hydrogen charging itself. So for a strain-induced, however, for a strain-induced martensite, time and pressure is significantly reduced. For pre-charged material, diffusion out time for hydrogen should be very, very large compared to the test time. Otherwise, if the test time is longer, hydrogen will diffuse out and effect of hydrogen will not be captured. So this method is not suitable for carbon and low alloy ferritic steels or materials where diffusivity is higher than 10⁻10 meters per second. So I think various forms of hydrogen embrittlement have been reported in literature. I have just considered only 3 of them. First one is hydride embrittlement, second is dissolved hydrogen embrittlement, and third one is hydrogen attack. In case of hydride embrittlement, this embrittlement is caused by the formation of hydride precipitate. In case of steels and all, this hydrogen embrittlement is caused by the dissolved hydrogen in the matrix. And third one is that hydrogen attack, which occurs during service, where hydrogen can combine with other interstitial under the operating condition, and that can cause embrittlement. Hydride embrittlement is exhibited by metals like zirconium, titanium, tantalum, niobium, uranium, thorium, etc. And common steel and all, they show dissolved hydrogen embrittlement. And hydrogen attack, I said, it is some types of iron and steel based materials at during operation in power and process industry at a temperature about 500 degrees Celsius. So exhibit this kind of failure. If you look at the mechanism, hydride formation and fracture. So here hydrogen diffusion takes place under the chemical potential gradient. And once the local solid salt is exceeded, hydride formation takes place. And here some experimental evidence is there that if you see a fractured surface, then hydride is observed on both the halves. So it means that it is a hydride which cleaves apart, not the debonding of the hydride and the metallic matrix. So both gross and localized hydride embrittlement is exhibited by metals like vanadium, zirconium, titanium, niobium, tantalum, and uranium. So suppose you have got a notch. Because of application of load, there will be stress concentration. Because of concentration, hydrogen first will migrate toward the crack tip, and here hydrogen concentration will increase. Once hydride precipitates, then what happens? Brittle hydride has formed over near the crack tip. Hydrides are brittle, so crack will grow through it, and then again it will wait for the hydrogen to move to the crack tip. So this is the mechanism of delayed hydride cracking. Now, second mechanism, hydrogen enhanced decohesion. This is observed in the mostly iron and steel. So here hydrogen decreases the cohesion across certain cubic cleavage planes. High hydrogen concentrations are there at the trap sites. Computational works also support this kind of bond weakening. So here again, suppose there is a notch, first hydrogen accumulation will take place, that will weaken the bond and the crack will grow through that. The third one is that hydrogen enhanced localized plasticity. Here hydrogen diffusion near the crack tip takes place, promoting the dislocation activity and microvoid formation and coalescence resulting in failure. In situ TM observations experimentally support this, the movement of dislocations in thin foils, which is exposed to hydrogen gas. Softening and strain localized in bulk space under some condition has also been observed. So this is what the dimple fracture surface is observed in this kind of thing. So plastic zone without hydrogen and the plastic ion with hydrogen where voids has already formed. And hydrogen attack, in fact, all these three methods, origin has got into the manufacturing practice itself. So if the initial manufacturing takes care of hydrogen, then mostly it can be avoided. Then we have to worry only about the service condition. Our hydrogen attack takes place during service, where it is the hydrogen induced embrittlement, all these things are all taking place during a startup and shutdown, especially at low temperature. So here hydrogen reacts with industries like carbon, nitrogen, and sulfur at elevated temperature. And fracture surface is marked by dimples. Low alloy steel piping and pressure vessels, copper containing oxygen exhibit this kind of failure. So mechanical properties which degrade because of hydrogen-induced embrittlement. So tensile properties, here both a smooth and non-tensile samples are used for evaluating the tensile properties. Beyond a critical concentration, it is strain rate independent. At low hydrogen concentration, it shows strain rate dependence. It requires a minimum volume fraction of the embrittling phase and strain rate independent. Oh, sorry, for hydride embrittlement, okay, we'll go one by one. So for hydrogen embrittlement, I think beyond a critical concentration, it is strain rate independence. However, at low concentration, it shows strain rate dependence. The fracture toughness is also getting affected. Again, beyond a critical concentration, it is strain rate independent. And in low hydrogen concentration shows strain rate dependence. At constant load, also hydrogen-induced delayed cracking is observed. Impact toughness also does not show good correlation. Impact and fracture toughness does not show good correlation because of the strain rate effect. Now, fatigue life also gets affected by hydrogen. We'll have some illustration on this. Creep, usually hydrogen is not a major concern because creep is also at elevated temperature. However, low strain rate and temperature, it could affect the creep properties also. On the other hand, hydride embrittlement requires certain minimum volume fraction. And since hydride is the one which is causing this in hydride embrittlement, so that's why it is strain rate independent. It requires again a certain minimum volume fraction. It is again fracture toughness is also so the strain rate independent behavior. Delayed hydrocracking, as explained earlier, is caused by hydrogen migration near the crack tip under the stress, hydrostatic stress gradient. Impact toughness is also getting reduced and it is orientation dependent. I hope we'll have some illustration on this. And hydride is also known to decrease the fatigue life, especially at low temperature. Again, I think hydride, what happens in case of hydride forming metals, hydrogen can be present either in the dissolved condition or it could be present in hydride. So dissolved hydrogen increases the creep rate marginally, but hydride decreases creep rate. That too, I think not that much secondary. That too is also marginal only. Now here are some of the illustrations of hydrogen-induced embrittlement. If you see applied stress to and time to failure, so as the hydrogen concentration is this thing decreasing, you can see this curve will become almost horizontal. So this shows the effect of hydrogen. So if the hydrogen is present, even at low stress, this component can fail. The fracture stress also shows here effect of a strain rate. At lower strain rate, you can see fracture. This thing toughness is very low, fracture stress is low. In the unembrittled condition, you have got this dotted line showing this thing, and because of hydrogen, this has come down. Here, log of crack velocity with the stress intensity factor is shown. Though threshold stress is not getting affected, but here I think a plateau region crack growth rate is increasing with increase in hydrogen concentration. And here it is this thing stress intensity factor range. Here threshold is getting affected. And in air, the curve is like this. In the hydrogen, the curve moves toward the left. Means crack growth rate has also increased, and the threshold stress intensity factor range that also got reduced. So here, hydrogen pressure effect is shown. Here, the threshold stress intensity factor as a function of hydrogen pressure is shown. As the hydrogen pressure is increasing, which the threshold stress intensity factor is reducing. So here, temperature effect is shown. I think at low temperature, hydrogen embrittlement effect is not there. Again, at higher temperature also it is not there. It is the intermediate temperature regime where hydrogen embrittlement effect is observed. Here, strain range cycles to failure is shown. Effect of hydrogen, you can see the curve shift toward the left. Creep also, I think, to some material like in this margin M246 still is getting affected. So this is the behavior in helium atmosphere, and this is the behavior in hydrogen atmosphere. So I think that's all I wanted to share with you about this hydrogen economy and my concern about that. So my recommendation for future research in the CRW, hydrogen is known to cause embrittlement in steels and hydride forming metals, which can lead to early failure of components used in hydrogen economy. The conditions that will prevail in hydrogen economy that will span from -20 20K to 273K, 1273K, and pressure could be as high as 140 MPa. So expansion of hydrogen economy need to be accompanied by extensive work on materials behavior characterized under cyclic loading, because just even without hydrogen, with this kind of pressure cycling and this thing pressure release will cause fatigue loading because of pressurization and depressurization. So the material which will be used in the hydrogen economy, they must be characterized for their fatigue life. The material which are known to exhibit hydrogen embrittlement, on them lot of work is there. However, investigation need to be extended to the conditions which will prevail in hydrogen economy. Data on hydrogen solubility, diffusivity, stress-free transfer sustains, partial volume, all these things are required for deeper understanding of hydrogen or hydride embrittlement. So all those new material on which this which we use in hydrogen economy, these data has to be generated. New materials like ceramic, polymers, metals, and alloys need to be investigated for their susceptibility to hydrogen embrittlement. So Jaya, I think it is okay. We can take some questions now, or shall I continue?
I think we can continue unless somebody wants to ask questions specifically on this section. I would request that we continue the talk and we'll take all the questions at the end. If that's okay.
Okay, fine. So now I'm coming to the work which we have done in BARC, and I picked up, I think, 5 issues in this. I think 5 issues on this, and one example I have taken that this will show that what is the length of a scale, what is the length of a scale which is traversed, which is covered by this hydrogen embrittlement in zirconium alloy. So first we'll talk about a stress-free transformation strain. Second is effect of hydrogen on tensile and creep properties. Third is delayed hydride cracking. And finally, it is fracture and impact toughness. And ultimately, how these properties are being used for assessing component failure, its life extension, and all. And finally, I will summarize this part. Now, once hydrogen in excess of solid solidity precipitates out as hydrides in metal like zirconium, titanium, niobium, barium, etc. A stress-free transformation strain decides the shape of the hydride precipitate for solid state transformation. We all know from our basic physical metallurgy in 3D Cartesian coordinate system, if the 3 orthogonal transformation strains are equal, we end up with a spherical precipitate. And if they are equal in 2 directions and less than 3rd direction, we end up with a plate-shaped precipitate. And if it is lower in 1 direction compared to other 2 directions, then we end up with a needle-shaped precipitate. In case of zirconium hydrogen system, hydrides exhibit a plate-shaped precipitate. So what we did is that we tried to compute this stress-free transformation strain. And here we have got alpha zirconium, which is having hexagonal closed packed structure. And we have got delta zirconium hydride, which is having a face-centered cubic structure. So what happened in 1973 Journal of Nuclear Materials, one article was published by Carpenter, G.C. Carpenter. And what is suggested is that one can determine this stress-free transformation strain by determining the radius of the zirconium atom and zirconium atom in hydride and alpha SCP phase. So if you see this zirconium crystal structure, it is having C by ratio less than ideal. So as a result, he assumed this ellipsoidal shape of zirconium atom. And in case of hydride, since it is having a face-centered cubic structure, so here we can assume a spherical shape of atom. And then based on semi-major and semi-minor axis of zirconium atom, one can calculate the transformation strain. The transformation strain E11, that is the one which is along the hydride platelet, and the transformation E22, that is along the normal to the hydride precipitate. And so whatever stress-free transformation strain is determined from this thing atomic radius at using atomic dimensions, that is valid for hydride precipitate. So this thing in Yamanaka et al. In June 2005, they published the lattice parameter of zirconium hydride up to higher temperature. So I just extended this methodology and determined this thing transformation strain of zirconium hydride as a function of temperature. So here we saw the lattice parameter of both alpha and A and alpha hydride and alpha phase. And from this, we determine EP1 and EP22. So here E11 is here. So as you can see, with the increase in temperature is increasing. And similarly, E22 also increases with increasing temperature. So using this, one can calculate, I think, what is the stress-free what is the accommodation energy of hydride in matrix. So to give some numbers, the formation of delta hydride is associated with increase in volume of about 17 atom% at room temperature and increases to about 20% at 300 degrees Celsius. Such a large change in volume results in local plastic deformation. Metal hydride system tries to minimize the strain energy. And the next few slides will show how the minimization in strain energy govern the shape and habit plane of hydride. So here what we do is that suppose we start with a spherical hydride, then you have got a strain energy per unit volume of this thing hydride. So here it is very high. As you go on making it oblate and oblate, this energy is accommodation strain energy reducing. But we cannot go on making it flat like this, because once it becomes oblate, interfacial area is increasing. So at some point there is a balance between the interfacial energy and the strain energy. And usually I think 20:1 aspect ratio is observed for hydrides. So this curve is for elastic, using elastic property of both hydride and the matrix. And this for using elastic property of hydride and matrix. In both the cases, conclusion remains same, that a oblate, flat, thin sheet of hydride is having lowest strain energy. The second illustration is that here, suppose you have got a hexagonal zirconium crystal. This rectangle is representing hexagonal zirconium crystal, and you have got a hydride plate like this. Now this green line you are seeing here, that is the basal plane, lying in the basal plane, and 001 is the normal to the basal plane. So what we did is we tried to calculate the strain energy of the whole system by assuming hydride orientations between 0 to 90 degree. So at every 15 degree interval, we had the orientation, calculated the strain energy, and the plot is shown over here for elastic case. You can see at 0 degree we have got minimum in strain energy, and as your angle with the basal plane increases, the strain energy also increasing. So this suggests the common interface between hydride and matrix is the basal plane. So this is for again for elastic case. For elastoplastic case also, the cases are nearly similar only. So hydride precipitation is governed by crystallographic texture, prior strain and stress. Suppose this is a section of a tube in which two orientations, this basal pole texture is like this. It is about 55% along circumferential direction, 43% along radial direction, and hardly any basal poles along axial direction. So what this means is that crystallography, there are two orientations possible. One could be this orientation, which is shown called circumferential hydrides. So these circumferential hydrides. And another orientation could be this is called radial hydride. And this radial hydride is normal to hoop stress. So that's why it's on red color. It is most deleterious. However, the circumferential hydride, even though it is hydride, but it's not that deleterious because its major dimension is parallel to hoop stress. So it doesn't cause significant embrittlement. The effect of hydrogen on tensile property is shown over here. Lot of curves are there, but I think if you see that ultimate tensile strength and total elongation is plotted here as a function of hydrogen concentration. And this boundary you are seeing, that boundary is cyan color, that is changing because the temperature of test is changing from 25 to 300, 350, 400, 450, and 600. As a result, dissolve of hydrogen concentration is changing. So since as I said earlier, in case of hydride forming metal, depending on the test temperature, part of the hydrogen will present in solution and part of the hydrogen will present at hydride. So the cyan color is the region in which hydrogen is present in solution, and this thing dark color is the region in which hydrogen is present at hydride. So you can see that when hydrogen is present in solution, my ultimate tensile strength has got reduced. But when hydrogen is present at hydride, there is a marginal increase in ultimate tensile strength. And this is consistent even at 400 degrees Celsius. You see UTS is decreasing with dissolved hydrogen concentration. However, in case of when hydride is present, it is marginal increase is there. Same at 450, same at 600 degrees Celsius. If you see total elongation, it shows the reverse behavior. Of course, hydride causes embrittlement, so ductility is getting reduced. Now, another plot is for creep properties, effect of hydrogen and creep properties. Here, this test is still our unpublished work. We have been able to complete this test at only at 400 and 450 degrees Celsius. Again, here same color code has been followed. If you see that cyan color region, here again dissolved hydrogen is increasing a minimum creep rate marginally. And in case of hydride, it is reducing the minimum creep rate. Here in case of 450 degrees Celsius, the effect is not much, almost horizontal lines are there. Now coming to delayed hydride cracking, it is caused by hydrogen migration up the hydrostatic stress gradient. Near the crack tip, hydride precipitation takes place. For pressure tube material, this hydride precipitation is having radial orientation. this radial hydride grows to a critical size, and once it attains the critical size, it fractures and growth of crack takes place. And this whole process repeats, and the cracking of hydride is delayed by the time required for hydrogen to diffuse to the crack tip, form a hydride of critical size, and that's why it is called delayed hydride cracking. The evidence for this comes from this fracture surface also. Fracture surface is marked by striations, that is alternate bands of bright and dark region. And this bright region, they are because of the ductile tearing of the matrix, and the dark region in between, that is because of the cleavage of hydride. So here, I think if had hydride and matrix debonded on the fracture surface, at least some portion we have got only bright region only, but this is not the case. So this suggests that it is a hydride which cleaves apart, and the bonding of hydride and matrix does not take place. If you see this DSC behavior is characterized by two important parameters. One is the delayed hydride cracking velocity, another is threshold stress intensity factor. If you see the plot of delayed hydride cracking velocity as a function of stress intensity, a threshold value is observed below which this delayed hydride cracking velocity is insignificant. And as you increase the stress intensity, initially DSC velocity increases, and then we attain a plateau region where this DSC velocity is independent of stress intensity factor. These four curves are obtained at different temperature. At lower temperature, we have got lower DSC velocity, and as the temperature is increased, plateau DSC velocity also increases. Now, why this during this plateau regime, why this DSC velocity is independent of the stress intensity factor? For that, we did some calculation. The main driving force for hydrogen migration is hydrostatic stress. So if you plot the hydrostatic stress as a function of the stress intensity, and this is for material of different yield strength, you see that beyond a stress intensity, what happens that plateau, the hydrostatic stress is constant now. With further increase in stress intensity, only plastic zone size increases, and hydrostatic stress is not getting affected, and which is the driving force for hydrogen migration. That's why, depending on the yield strength or temperature of the material, this plateau region is observed, where DSC velocity is independent of the stress intensity factor. Here we saw, I think, a plot of material from different sources. Both our material and CANDU pressure tube material are almost overlying. Here, the first two curves, they're almost overlying on each other. Whereas the Russian material, which is produced by heat-treated tube, it is having almost half to 1/3 DSC velocity. This striation spacing, this striation spacing with yield strength is shown over here. As the yield strength increases, this striation spacing reduces. That is what this curve shows. Now, fracture toughness. So I think again, hydrogen, this thing is important over here. The DM represents the double melted material, and QM represents the quadruple melted material. This initially pressure tubes were being manufactured by ingots produced by double melting, and you can see here that we have tested the material up to 100 ppm, and all the three curves are lying almost overlapping with each other. So no significant embrittlement defect is observed. However, when we did the same thing on the tube produced from quadruple melted ingots, at the room temperature, you can see that initially toughness is very high. By adding 25 ppm hydrogen, there is a sharp reduction in fracture toughness, and after that, with further increase in hydrogen content, there is no change in fracture toughness. As you go to higher and higher temperature, the effect of hydrogen is getting reduced. Now, this is another illustration that we did some FEM calculation of the stress field in the hydride and the matrix surrounding it. And what we saw is that this thing, depending on the nature or tendency of hydride to grow or shrink. So during, I think, heating, what will happen that hydride will shrink, it will contract, whereas during cooling, hydride will expand, it will precipitate out. So during cooling, you'll see that inside this is a boundary you can see here. So this is my hydride, and I've transformed into, from initially it is zirconium, then transformed into hydride, and this is surrounded by matrix. So we did this calculation. We see that inside the hydride, we have got compressive stresses, and just outside this, we have got tensile stress in the matrix. However, when you heat it, when you just same sample, you just dissolve it back, what you get is surprising. Now, in this case, what happened that this hydride, now inside the tip of hydride, you have got a tensile stress, and the matrix just outside the stress, nature of the stress has got reduced. So these calculations were done at various temperatures. This dotted line shows the contraction lines, and solid line shows the expansion line. And we thought, I don't know whether this is just FEM calculation, we have got some numbers, or whether it will have any effect on fracture toughness. So here we show the plot of J parameter with the delta A. For heating curve, you can see J curve is like this. For cooling curve, it is like this. And in fact, the plot of this J max with test temperature is shown over here. At lower shelf and upper shelf, the difference is not much, but in the tension regime, both heating and cooling is having some effect on fracture toughness. You see the fractograph also in case of cooling, what is happening is that number of axial splits on the fracture surface is very low. In fact, these lines you are seeing, they are called axial splits. They are because of circumferential hydrides. Because of axial split of a stress, these circumferential hydrides cleave apart and they give features like axial splits. But in case of cooling case, you see number of axial splits are much lower. So what we propose is that suppose there is axial split, then first axial split takes place, and then deformation gets localized in the ligament joining these two axial splits, and that results in the lowering of the fracture toughness. So in order to summarize, I think, in fact, here I think I remember that Arthur Mota's group from Pennsylvania State University, they used our stress values to calculate the lattice parameter of hydride at same temperature by attaining the temperature by both heating and cooling. And they did find that hydride lattice parameter is a change depending on the direction of approach of temperature. So finally, I think some observations. So a stress component inside hydride normal to hydride platelet during heating, that is shrinking, it is tensile in nature. So if a tensile stress is inside the hydride, it will favor axial splitting and may result in increased fracture toughness due to delamination. So in fact, we did observe larger axial splitting in case of heating case. However, during cooling, it is compressive in nature. So there is no axial splitting. So it will suppress axial splitting. A stress component inside matrix normal to hydride plate. It is compressive in nature for heating case. Prevent the crack growth through matrix. May result in increased fracture toughness. However, in case of cooling, the inside the matrix now it is tensile in nature, which facilitate crack growth through matrix. It may result in reduced fracture toughness. And consequence of axial splitting is that it will cause localized deformation in ligaments joining axial splits. It may lower the fracture toughness. Whereas since no axial split is observed in case of cooling case, chances of localized deformation are minimized and may result in higher fracture toughness. So ultimately, axial splitting and localized deformation that is affecting the fracture toughness. So that's why in case of heating case, we are ending with lower fracture toughness. Here we show the effect of orientation. So these red lines and blue lines are shown the hydrides. So we considered here 8 permutation and combination of hydride platelet orientation with respect to crack plane. And the summary is that if hydride platelet is oriented parallel to the crack plane, there is drastic reduction in fracture toughness or impact toughness, especially at lower temperature. As you go to higher temperature, toughness improves. However, if hydride platelet is oriented normal to the crack plane, toughness is not that much reduced. Now we determine this fracture toughness parameter, but what do we do to it? So these data are required for safety assessment. Here, I think there is a parameter called operating pressure. We all know that coolant water, heavy water is used in pressurized heavy water reactor. And this thing, in order to attain, I think, higher heat extraction, we want to maintain the heavy water in the liquid phase. For that, we have to pressurize it. So lower bound pressure is decided by the steam table, that you have to keep the water in liquid state. However, upper boundary is provided the fracture toughness of the material. So in case of this thing, as the residual material, you can see this solid line at the top. So you got sufficient safety margin. However, as hydrogen pickup takes place, hydride precipitates, and depending on hydride orientation, we will have this fracture toughness values getting reduced, and especially if it is getting reduced the reactor operating temperature, this safety margin getting significantly reduced. So especially radial hydrides, you can see here, if the radial, these are all hydrides with the radial orientation, and you can see that the boundary provided by the metal property is coming very close to the operating pressure regime. So in such cases, these tubes cannot be operated. These tubes need to be retired. Now, another concept for pressure tube design is the leak before break. It is a fail-safe criteria based on fracture mechanics. there are three levels of LBP. The level 1 is assume that there is no crack in the material, so it is inherently safe to operate the tube. But we all know that during manufacturing, some flaws invariably will be present. So level 2 assumes the presence of a surface crack, but we assume that there is no growth of the crack. However, as we have seen that under operating condition, delayed hydride cracking can occur, and that can result in crack growth. So level 3 assumes a crack, but assumes that leak size crack should not be more than the critical crack length. So flaw size of less than 2% wall thickness is permitted during manufacturing. And this thing we determine the CCL by estimating the crack driving force under the operating condition. And in-service crack mechanism delayed hydride cracking velocity is there. So by using this fracture toughness, CCL obtained from fracture toughness and DSC velocity obtained from delayed hydride cracking test, one can assess whether these tubes will fail by leak or by break. So here it is shown here. This is the JQ parameter obtained experimentally, and SH is the hoop stress, sigma flow is the flow stress of the material, and this thing foliage factor M is there, which is a relationship between this thing, tube geometry and crack size and all. And here operator response time is the one which has to be less than the time required for a leak size crack to exceed the critical crack length. In the denominator, you have got twice the DSC velocity, because crack can go axially in both the direction. Here we show a plot of a critical crack length with test temperature. For the as received material, this dotted line is here. For the material containing 100 ppm of circumference hydrides, you can see a solid blue line is there. And for the material containing 100 ppm of radial hydride, almost up to reactor operating temperature, the fracture toughness is very low. So radial hydrides are not desirable thing. But then this data can be used. So CCL is affected by hydrogen content, hydride orientation, microstructure and texture, and hoop stress, flow stress, Young's modulus, and component geometry. The CCL and BSDC is required for validating the LBP criteria. If a leak size crack is less than the CCL, leak before break will occur. However, if a leak size crack is greater than CCL, break before leak will occur, which is not desirable. So finally, I come to the conclusion of second part. The multi-scale structure mechanics starting from atomic level to component level was illustrated through various aspects of hydrogen-related problems of zirconium alloys. Using this approach, not only the underlying regression mechanism can be understood, but valuable input for designer and safety engineers can be obtained. I would like to thank my colleagues for their contributions, Bind, Saurabh, Avinash, Murthy, Yatindra, for creep work, Kapu Sarkar, Chandan Sibe, Rishi Sharma, Vivek Patel, and Numidra Chatterjee. I am grateful to my mentors, Dr. Tiki Sinha was my first boss, Professor BP Kashyap, my PhD supervisor, Dr. Madan Gopal, Dr. Day, Dr. Banerjee, and my mighty host, Professor Stale. Support from my senior colleague, Dr. P.K. Day, Dr. Suri, Dr. R.K. Sinha, Dr. Anil Kapotkar, Dr. Chakravarti, Dr. Denis Srivastava, Dr. Ramanujam, Dr. Placid Rodriguez, K.C. Sau, Anantaraman, V.K. Sa, Sri S.A. Bharadwaj, Kit Coleman, Manfred Pulse. It was very useful. And support from organization is thankfully acknowledged. Thank you for your attention.
Thank you so much, Dr. Singh. I think you covered a lot of aspects today, beginning with the hydrogen economy and starting from hydrogen generation all the way to storage and the embrittlement causes and material selection. Plus, of course, specifically the effect of hydride as well as dissolved hydrogen in zirconium alloys. So the talk is open for questions and discussions. So I'll go with the calling out the names as and when people raise their hands. Unfortunately, the first one to raise their hand is an unknown user. So yeah, the unknown user can speak and introduce themselves.
I don't know if I'm the unknown user, but thank
Okay,
you,
that
Dr.
was
Singh, for
Vikram,
very comprehensive review. I had two questions. I'll just ask one now. The striation spacing between the ductile region and the cleavage in the delayed cracking, is that because you're exhausting the hydrogen from a certain region in front of the crack tip, and so you need time for it to accumulate once again, and that's why you get a ductile band and once again cleavage and so on?
Yeah, in case of this thing, delayed hydride cracking, what happens, it is a localized form of hydride embrittlement. What happens is that total hydrogen concentration is has to be between two parameters. These are terminal solubility for dissolution and terminal solubility for precipitation. If hydrogen concentration is more than terminal solubility for precipitation, then DSC velocity does not depend on hydrogen concentration. Now coming to your question, that when hydrogen concentration is whatever hydrogen is there in the material, it should be in dissolved condition, or it could be present at hydride also. So hydride, which is hydrogen which is present as hydride, that only acts as a source of hydrogen. So in case of DSC, what happens in the crack plane, we need that radial hydride formation, because circumferential hydrides are normal to the crack plane. So because of hydrogen migration, first hydrogen accumulation near the crack tip takes place. Usually it takes place in the region where maximum hydrostatic stress is there. And once solid that TSF is exceeded, then this radial hydrides form. And then this radial hydride will start growing in both directions, but already concentrated stress because the remote load is there near the crack tip. So near the crack tip, still because it is elastoplastic material, so their hydrogen accumulation has not taken place. It is still as received material. So when this ligament near the crack tip is unable to support the load, that time this snaps. So this ductile region, the bright region we are seeing near the thing, that is because the ductile snapping of the ductile matrix, and the darker region which you are seeing, that is because the cleavage of the failure of the hydride. So entire process repeats in a discontinuous manner. So that's why it is called delayed hydride cracking. I hope I am able to answer your question.
Yeah. Okay. So the hydrides are already there. It's just a sequence of rearrangement.
Yeah,
Okay.
it is rearrangement. It is present in the bulk, but it has to diffuse from bulk to the region near the crack tip, where higher hydrogen concentration will be there, where hydride precipitation will taking place with radial orientation. And once this radial hydride has grown beyond a critical thickness, then matrix is unable to support the concentrated load.
So is the striations thickness separation, does it have to do with any kinetic parameter?
Yeah, kinetic, more than kinetic is the strength of the material. For a low strength material, this steady-state spacing is much wider. Of course, kinetics is there in steady-state also, because if you go to higher temperature, then steady-state spacing increases. Again, that is an indirect effect of strength only, because we go to high temperature, the strength will be lower.
Thank you.
Yeah, Deepa.
Yeah, thank you. That was quite amazing how you covered the first half with some case study, a large, vast topic. I had a couple of questions. One on slide 17 about, could you throw some light on the 4 different methods you showed, and how do you actually decipher and characterize it? And the second question was a little more futuristic in the sense, what are the, what are the state of the art testing, that is mechanical testing, standard ASTM that is being done, specifically using hydrogen environment, which is different from just characterizing the exposure.
I think this slide 17 you're telling, no?
Yeah, I was just wondering, how do you, how do you characterize all these, when you're looking at a fracture surface, or how do you pick signatures from, hydrides? I can understand if it actually forms in the wake of the crack path, but how do you detect, what are the characterization methods to detect the presence of hydrogen and the embrittlement because of that?
Yeah, you rightly said, in case of hydride forming metals, the conducting experiment is much more easier. In fact, for zirconium alloys, we determine this DSC velocity regularly. There, what happens, hydrogen does not come out of the metal system so easily. So in fact, if you recollect, there is something called pressure composition isotherm. So it shows initially it will increase that on y-axis you got partial pressure of hydrogen, on x-axis will have concentration of hydrogen, and initially it will increase linearly, then it will show a plateau, and then again it will start increasing linearly. So this plateau pressure is the one which will decide that if partial pressure outside the sample is more, in that case hydrogen will go from environment to the metal, and if partial pressure is less than the plateau pressure, in that case hydrogen will come out of the system. So for those who are doing testing in hydrogen atmosphere, they should be aware of this pressure composition isotherm for hydrogen and metal or alloy system. And if you want to see the effect of hydrogen embrittlement, you should ensure that the pressure, partial pressure of hydrogen is more than the plateau pressure. So for different system, this plateau, this pressure composition isotherm is available in literature. One can start from there. And since in case of zirconium, I just said that since hydrogen does not come out, so that is another concern. However, in some titanium alloys and all, especially if you treat it in a vacuum and all, then this will come out, and there it becomes a issue. Similarly, for the iron and steel and all, this thing hydrogen can diffuse into the metal, and it can diffuse out also very quickly. So one has to be cautious that, especially this pre-charging and all, though people do this electrolytically pre-charge the steel sample with hydrogen, and there is a long delay, between the testing and charging, then effect of hydrogen will not be captured. So in case of a steel, of course, so you can, in fact, in all metals, one can go for hydrogen concentration analysis. However, in case of a steel, again, hydrogen concentration will also depend on that when hydrogen loading has been done, in what condition it has been stored, and when actual testing is done, whether hydrogen is present or not. So here some suggestions are there. Usually people, moment people charge it, they will dip in liquid hydrogen. The sample will dip in liquid hydrogen so that hydrogen does not escape. Second thing, you can have some FCC like nickel or copper coating on that so that hydrogen does not escape. And of course, computational solutions are there for hydrogen enhanced decohesion, the second mechanism. So computational support has shown that yes, bond weakening take place if dissolved hydrogen is present.
Thank you. Thank you.
Did I answer your question?
Yes, that, I mean, I think it's a vast topic, but thanks for throwing light on the pressure diagram to look out for. I mean, the second question I quickly had at Jaya's, okay, and I can ask is, what are the measures being taken to consciously test, mechanical testing in the presence of hydrogen, given all the futuristic as a fuel, as a gas, and what are the differences between a testing in an atmosphere and hydrogen, and how is it being documented? Are there test setups that are put in place for?
Yeah, I think if you see this thing around, I think 2009, few countries they set up labs, or they formulated specific programs for determining the susceptibility of hydrogen to different metals and all. And Sandia National Lab in US, they are the one who are leading this program. They have set up facilities for material testing hydrogen atmosphere. In fact, there are several challenges in that, because I think the lab in which they want to test the materials under hydrogen atmosphere, I think it has got a shock resistance sensor, all those things will be required and all. So that sensor development for this kind of testing is altogether different. So, but our, I think, concern is that as far as hydride embrittlement is concerned, you don't need any specific facility. A normal mechanical facility with hydrogen charging and this thing, sample geometry and all, whatever conventional geometry that can be used. Major concern is coming for this thing, testing metals like austenitic stainless steel, where this, in order to pump in hydrogen into the metal, you need a hydrogen pressure of some 100 MPa and all. So for that, a specific facility is required. In fact, another thing, this thing could be considered is that pre-charging, but again, pre-charging, the fugacity is very high. So in our country, I think we still need to have, in my opinion, we still need to have a comprehensive approach to this. Piecemeal efforts are being put in by different laboratories. But if we are going to embark onto this hydrogen economy, in my opinion, I think, and plus this Indian Structural Engineering Society, the right forum to propose to have a national facility for evaluating the hydrogen embrittlement of materials.
Thank you. Thank you very much. Thanks, Jaya.
Yeah, Dr.R. Singh. Next.
Yeah, good evening, sir. I'm Ratnakar Singh. I'm Ratnakar Singh, a postdoctoral fellow under the Professor Vikram Jairam sir and Professor Praveen Kumar sir. Sir, actually, I am also started working in this hydrogen embrittlement phenomena. So my question is that what type of materials we are being used for hydrogen storage materials? What are the suitable materials that we can?
See, I think as you saw in case of this thing right now, hydrogen which is being used, that is being used in cylinders. So for cylinder, we have got aluminium, we have got steel, we have got composite materials, we have got polymer liner. Plus, if you are saying this thing, your hydrogen stations, gas stations and all, recently I found some work on this thing, polymers, rubbers, especially the gaskets and seals, which is used for dispensing hydrogen. They're also susceptible to hydrogen embrittlement. So I think all kinds of metal, whichever metal is going to be used. Right now, since your gaseous hydrogen and liquid hydrogen, that is the one which is being used. So in aerospace application, you see titanium alloys are being used. In zirconium, we are using DAE. So I think depending on in what form it is stored. So two things are there. One is storage material is one, and another is that how it is produced. In every stage of hydrogen economy, that is whether it's production or it's a storage, transportation, consumption, whatever material comes in contact, a comprehensive this thing work needs to be carried out. Steel, of course, I think steel, as I mentioned, that for austenitic stainless steel, this hydrogen embrittlement occurs at very high pressure. But then I think some suppose the strain-induced martensite formation is there in some grade of austenitic steel, then the pressure and the temperature requirement for this thing embrittlement comes drastically lower.
Okay, right, sir. Sir, my second question is that how temperature is affecting that hydrogen embrittlement? Because one of your slides you have shown that at higher temperature there is some embrittlement and creep and cutting behavior. But sir, at high temperature the hydrogen will degas out. So how it is affecting that?
So usually this thing for steel and all, hydrogen embrittlement is not reported above, I think, 250 degrees Celsius or so.
Yes, right.
Because at lower temperature only hydrogen embrittlement is observed. At very low temperature, you can imagine that hardly any hydrogen will be present in solution. So that's why probably its embrittlement effect is not there. As you go to high temperature, some hydrogen will be in solution, and if it is causing decohesion, then I think embrittlement effect will be observed. As you go to higher and higher temperature, probably this decohesion effect is not there. Only in case of hydrogen attack, which occurs at 550, 600 degrees Celsius for materials used in the process and power industry. There, this kind of embrittlement is observed. And there it is not because of hydrogen, it's because of combination of hydrogen and this thing, some other interstitial like carbon, nitrogen, sulfur and all. And this thing, if you see earliest mechanism of hydrogen embrittlement, which was proposed for this thing, hydrogen embrittlement was that once hydrogen solid is exceeded, then hydrogen comes out and it gets accumulated in the voids, and under those so pressure will be very large, and that will rupture almost any material. The pressure inside those voids of the order of several lakhs of atmosphere will be there. But then when people thought that if that is so, then fractographic evidence must be there. And on fractured surfaces, completely cleavage failures were there, oriented at different angles and all. So then they discarded this theory. However, in case of hydrogen attack, fracture surface does show these dimples. So that is the experimental support for this. So I don't know. So can you just repeat your question? Whether I digress from there?
No, sir. Actually, what I have asked that at high temperature, how
you wanted the temperature? Why only? Oh, got it. You wanted only why
at high temperature that hydrogen will diffuse out from the material. Because
all it depends. As I say that, yeah, for hydrogen diffusing in or diffusing out, the most important parameter is your diffusing in or diffusing out. That depends on the plateau pressure from the pressure composition isotherm. If partial pressure of hydrogen outside is less than that plateau pressure, then hydrogen will diffuse out. And if partial pressure is less than that, more than that, then hydrogen will diffuse in. So ultimately, the plateau pressure of the pressure composition isotherm that will decide whether hydrogen will diffuse in or diffuse out. At higher temperature, what will happen that probably the lattice parameter also will increase. So how it will interact, how it will affect that cleavage energy. So that is how I think probably high, and most of the embrittlement mechanism at higher temperature, metal becomes more ductile, they become more tolerant. So that's why this embrittlement effect is not observed at higher temperature. In our case also in high rate form, you must have seen just at 250, 300 degrees Celsius, we are in the upper shelf, and there the fracture toughness is as good as the your as received material, even with a radial high rate orientation.
Okay. Okay. Thank you.
Vishwanath, you go next.
Thanks, Professor, for such a wonderful talk. I have two questions regarding this microvoid formation. Is it forming near the triple junctions or within the grain? Because you're saying that it is going to softening, but if it is forming inside the grain bond, inside the grain, and the dislocation activity, it would really increase the I mean, it would difficult for the crack to propagate. Can you throw some light on that?
Here when we talk about, you are talking about hydrogen enhanced local plasticity, no?
Yes.
Yeah, here I think we are talking about the inside the grain only. So what happens that dislocation and hydrogen is interacting, and because the presence of this thing hydrogen near the dislocation, especially edge dislocation, they are able to glide very easily. So local plastic deformation takes place. So in that first, wherever some stress radiators are there or something which obstruct the dislocation hydrogen atmosphere movement, there this microvoid formation will be there, and then ultimately they will coalesce. And as in case of normal failure microvoid formation coalescence, here also failure will take place. Now this localized plasticity, actually it is an embrittlement mechanism. What it does is that it localizes the plastic deformation in the or near to the crack plane itself. That's why the material fails in a brittle manner.
Fine. Can you around I think 37 slide or something, you have shown an inside groove crack. From the surface it would go through the thickness. The
Just
crack front is curvilinear.
Slide number
37, I guess 36 or 37.
37, just a minute. This one?
So this in this scenario, how do you really, where do you measure your I mean K, because it would have a mixed mode nature for this curvilinear front.
No, curvilinear, this crack is just a schematic to show that it is breaching the wall thickness. Usually these DSC cracks are very sharp. It is a planar, almost like a sharp planar crack. It is not a volumetric flaw. And for this, I think actual flaw will have some volumetric nature also, but safety assessment has to be done under the most conservative scenario. So under the laboratory, this is CCL and DSC velocity, all these things are determined by having a fracture toughness sample which is pre-cracked, and the way we do the fracture toughness test, we determine this CCL from the both material property as well as the operating condition like hoop stress, wall thickness, flow behavior of the material, flow stress of the material. And then DSC velocity is determined again by carrying the sustained load cracking test. There again, CT sample is used and which is subjected to a load which will give a stress intensity factor more than the threshold stress intensity factor. We are more interested in knowing the DSC velocity of the plateau region. So plateau region velocity is being used. So even though the pictorially it is shown very shallow crack, but for safety assessment, we need to do the material testing under the most conservative condition.
Thank you.
Prasad Reddy.
Hello, sir. Good evening. This is Reddy from ICGAR. Sir, are these hydrates are stable under neutron environment because they may undergo some like fragmentation and dissolution back to the lattice, or they are highly stable?
Yeah, I think beta phase, about that some report is there that under irradiation it dissolves reprecipitate. Hydrides, I think as such, once the hydrogen concentration is there and sufficient amount of hydride is there, at least I have not come across any report where hydride this thing dissolution or disintegration because of neutron radiation will be taking place.
Okay, okay. Because in the case of ODF steels, what some of the literature, what we have seen is that when they put up these ODF steels under neutron irradiation, so when the particle size is beyond some 20 nanometers, so it gets fragmented and the yttria goes back to the lattice. But since its dissolution is very less, it pops out and then again forms yttrium oxide. So it dissolves and reforms. Whether such thing is there in this
So
case
you are
also.
telling that nano size that yttria precipitate itself is dissolving.
Yeah, yeah. Beyond 20 nanometers, it dissolves. I mean, it gets fragmented and then finally it dissolves.
Okay. Now here
But
I
not,
think even in irradiated material, these hydrides have been observed. As such, I think at least I am not aware of any work where hydride dissolution. Of course, beta phase, lot of work is there. Beta phase dissolution under radiation and reprecipitation in some other location, and that work is there. Hydride, at least I have not come across where it will dissolve.
so these are size distributions. The hydrides have a particular size range, or the peaks at particular size normally.
No, it has got, it depends on cooling rate. This thing hydride formation is a hybrid transformation where this zirconium atoms rearrange like a martensitic transformation, and hydrogen is causing interstitial ordering in the transform matrix. So depending on cooling rate, in fact, in reactor we are getting only delta hydride mostly because of the this thing cooling rate and hydrogen concentration involved. But there are 4 types of hydride: zeta, gamma, delta, epsilon. And about epsilon hydride, lot of work has been done. I think Professor Vikram Jayaram and Professor Raghu and all may be aware. Dr. Banerjee's work, both deep energy and high energy, one in zirconium alloy, another is titanium alloy. And there I think this thing gamma hydride, initially it was thought it is a metastable phase. Nowadays I think there is support that no, it is also a stable phase. So all 4 kinds of hydrides are there. And like gamma hydride shows little shaped morphology, gamma hydride shows plate tape morphology. So most of the work which we are presented today is related on gamma hydride, delta hydride. And delta hydride size depends on cooling rate. Suppose you cool the sample where hydrogen is in solution very fast, you'll end up with a very short hydride. If you cool it very slowly, like furnace cooling and all, then you will end up with very long hydride. And it will depend on hydrogen concentration also.
Okay. Okay. Thank you, sir.
Yeah.
Yeah, there's a question in the chat box. You may want to ask them.
Sure. I will read it out. I think Dabu Prakash is asking this question. Thanks for an excellent lecture. Can you comment on the crack tip and crack wake modeling in the presence of hydrogen environment? I'm aware of some literature on crack tip chemistry modeling under static loading conditions, but not sure about cyclic loading conditions.
Okay, just wait. So the question is, I'm not able to see the question.
Yeah, should I will just read it out again to you. It's about the modeling.
Yeah,
okay.
Yeah, let me read the question, what I've understood.
Yeah.
So the question is that whether any work on the crack tip modeling.
Yeah, at the crack tip and crack wake under cyclic loading and hydrogen environment.
Cyclic loading, I don't think I have not come across any work. Usually this is all sustained load this thing cracking. You just take a sample which is pre-charged with hydrogen, and then I think this thing hydrogen migrates up the heterostatic stress gradient. If cyclic loading is there, I'm not sure so what will happen. So long as driving force is there, hydrogen will diffuse toward the crack tip. And if cyclic fully reversible cycle is there, then in that case it may diffuse out also from the crack tip, because hydrogen will like to move to a region where tensile hydrostatic stress is there. So cyclic loading, usually from reactor point of view, means it is not of much of importance for us. But of course, wherever I think thermal cycling is there, if suppose coolant is leaking and all, in that case, also I think it is a temperature gradient, but not I think that I think the therm.
And even
Look,
if there is pressure cycling of any. Sorry, Raghu Prakash is online.
Yeah, Dr. Singh, I'll just try to explain what I'm trying to get clarified. See, we have some students who have been able to decompose the, the crack growth due to the mechanical loading, and then the crack growth due to the environment.
Okay.
Okay, so basically the resultant dA by dN is sum of dA by dN mechanical plus dA by dt. Okay, now in this case, you are going to have the hydrogen environment that is going to result in dA by dt. Right. So if I want to do some kind of, what I call mechanistic model, which is just not mechanistic alone, but it couples the, the chemical interaction effect also, then, I need to know how to handle this, if it is a static loading or if it is a cyclic loading. Because if you look at the static loading, it's kind of relatively straightforward, or at least easier to handle, because you keep a crack wake and then you have the, the kind of species concentration, and then use some kind of Nernst Planck equation and then try to see what is the diffusion component of it and so on. Right. But if it starts cycling, the crack tip is, undergoing the, the compression, decompression, the crack wake, and then it also includes the transport species of the, the elements.
Here, I think you see,
So that's what I was trying to know, that, whether you have any, efforts in that direction, and, like, what is your thought on this?
See, in this case, even delayed header cracking, if you see that complete model of this thing, mechanistic model of delayed header cracking does not exist. At best, initially, people, what they have done, they have tried to predict the hydrogen concentration near the crack tip. Or even a stress analysis can be done in some way. But comprehensive model, which can model each step of delayed header cracking process. So some attempt has been made by, I think, Manfred Pools and his students and all. So what they have done, they have tried to marry this thing FEM simulation with phase field modeling. And with phase field modeling, so I think we are also with Professor Rajgopalan from IIT Hyderabad. We are working on a project together where we intend to model this DSC phenomenon, again using phase field simulation and with the FEM simulation. And there also what happens, lot of parameters are there, lot of material property parameters are there, which is not very easy to get. And whenever you do the modeling work, if those parameters are not explicitly determinable, in that case, it becomes a fitting parameter. So at least we are trying to just model this DSC part itself, which is under a static loading. Cyclic loading we have not ventured into, because even this DSC part is not yet fully modeled.
And just out of curiosity, is this a 1D modeling of the crack tip, or is it a 2D model or higher order?
In fact, we intend to do 3D model, but most of the models in literature is 1D model only.
Right. So that's what is my also observation, and I'm just trying to push some work along that, at least to make it as 2D.
If you want to push this, DSC is a very interesting phenomenon. And right now, the dispute in international community is that whether DSC process is a precipitation first process or diffusion first process. So one group of thought, one group of people suggest that when during DSC, when the load is applied near the crack tip, first this thing hydrogen diffusion takes place near the crack tip, and once hydride is precipitated, then crack load takes place. Whereas another group of people believe that first, as soon as this load is applied, then what happens? Hydride precipitates. When hydride precipitates, it will set up a concentration gradient, and because of which hydrogen migration will be taking place. So in both the cases, both diffusion and precipitation is required to take place, but which one is the first? Accordingly, model parameters change.
Right. So it's a path dependent.
Yes.
Okay, but do they take into account the effect of plasticity ahead of the crack tip?
Yeah, plasticity they are able to take, even not only plasticity, people are trying to factor in, because as I showed that when hydride is precipitating, it is having its own stress field also. So it is
Right,
not only
right,
the
right.
global
That's
stress
what is a
field.
coupling, right? Right,
Yeah, coupling.
exactly.
So that also people are doing.
By the way, just another question out of curiosity. Did you measure the, the crack tip chemistry using some kind of sampling technique or something like that during any of the studies?
In fact, as far as DSC is concerned, this is well-established process. We have not measured it, but we have got a problem. Suppose both hydrogen and deuterium isotopes are present. So hydrogen isotope is likely to diffuse much faster. So we intend to measure this thing, isotopic ratio of hydrogen, because if hydrogen is really moving fast near the crack tip, we must get higher hydrogen is to deuterium ratio. But so far we have not succeeded in that. Let us see.
Good. It was a very, what do you call, enriching lecture, and I really thank you for that.
Yeah, thank you.
Over to Jaya. Yeah.
Yeah. Thanks. Thanks very much for a very sort of lengthy discussion as well, that you patiently answered all the questions. I had some, but I think I will get back to you later. In the interest of time, we would like to thank Dr. Singh again for giving this fabulous talk, which covered the entire spectrum of hydrogen in materials. Yeah, I think we can all do virtual claps only these days, but yeah. Thanks a lot for joining, all of you, and for participating in this both the talk and the discussion very actively. So
I think
Dr. Singh,
we also will send the, kind of the certificate for the webinar soft copy. I think we'll send it across to Dr. Singh. Yeah, thank you.
Sure.
Yeah,
thanks a
thank
lot,
you very
Dr.
much
Singh,
from my side to all of you. And my apology that I thought it's from 5 o'clock, so I went to.
No, sorry, I should have pointed out.
Told me, no, it is 4 o'clock, so I came back.
I'm so sorry. I had to rush you back.
It is my fault. It's my fault that I did not notice it is 4 o'clock.
Thank you.
Thank
Thanks
you.
a lot.
Bye-bye. Keep in touch.
Yeah. See you.
Yeah.
Yeah, we will. Bye.